Generative AI is changing the world and transforming every industry, and if you want to stand out in your next interview, you need more than just answers. You need mastery. In this series, we're breaking down 100 of the most important generative AI interview questions so you walk in prepared, confident, and unforgettable. Let's dive in.
What is generative AI? Generative AI is a type of artificial intelligence that can create new content like text, images, audio, video, or even code, instead of just analyzing existing data. Traditional AI is often about recognition or prediction. For example, classifying emails as spam or not spam. Generative AI goes a step further. It learns the patterns and structure of existing data, then uses that knowledge to produce original outputs that resemble or extend what it has learned. Most modern generative AI systems are built on transformer-based architectures like GPT or diffusion models, trained on massive datasets using self-supervised learning. This allows them to generate results that are contextually relevant, coherent, and sometimes creative. We see this in real-world tools like GitHub, ChatGPT, Gemini, Copilot for Code, ChatGPT, Claude, Gemini, Copilot for Writing, and Midjourney, DALL-E, Bing Image Creator for Visuals. All examples of AI producing something entirely new based on what it has learned. How is generative AI different from discriminative AI? Generative AI and discriminative AI solve different problems in machine learning. Discriminative AI focuses on distinguishing between classes or predicting labels. It learns the boundary between categories directly from the data. For example, a spam filter that classifies emails as spam or not spam. Technically, it models the conditional probability P of Y by X, meaning it predicts the target given the input. Generative AI, on the other hand, learns the underlying distribution of the data itself, the joint probability P of X, Y, or just P of X, and can then sample from that distribution to create entirely new data points. For example, instead of just classifying an image as cat, it could generate a brand new, realistic image of a cat. In short, discriminative AI predicts or classifies generative AI, creates or imagines. We often combine the two. For instance, a generative model producing synthetic data and a discriminative model classifying it to get the best of both worlds. Explain the architecture of a typical generative model. A typical generative model architecture has three main stages: input processing, latent representation learning, and output generation, all tied together by a training objective that encourages the model to learn the data's underlying distribution. 1. Input processing. The model first tokenizes or encodes the input into a machine-readable format. For text, that means word or subword tokens. For images, pixel arrays or patch embeddings. 2. Latent representation learning. This is the core of the model. In modern architectures, transformers dominate. They use self-attention layers to capture context and relationships across the sequence or image patches. Older generative models used RNNs or LSTMs for sequences, or CNNs for images. Diffusion models and VAES learn compressed latent spaces to sample from. Third, output generation. The latent representation is decoded back into human-readable content. Words for text models, pixels for image models, or audio waveforms for speech. Sampling strategies: greedy search, beam search, temperature, top K or top P. Control creativity and coherence. Fourth, training objective. Most use self-supervised learning, predicting the next token for text, or denoising an image for diffusion. Loss functions vary: cross-entropy for language models, reconstruction loss for autoencoders, adversarial loss for GANs. Example: GPT style, LLM, Encoder-decoder. No, decoder-only transformer. Input tokens. Embeddings, stacked self-attention plus feed-forward layers. Output logits. Sampling. Generated text. Example. Diffusion model. Starts with random noise. Denoising steps guided by a neural network. Final image. In short, a generative model is an encoder plus transformer or diffusion core plus decoder, trained to model data distribution so it can sample new, realistic content. What are the main applications of generative AI? Generative AI has a wide range of applications across industries because it can create new, high-quality content in many formats: text, images, audio, video, and code. Some of the main applications include 1. Content creation and assistance AI copilots in Microsoft Word or Excel for drafting, summarizing, rewriting. Blog or article generation, marketing copy, social media posts. 2. Code generation and software development, GitHub Copilot suggesting functions, writing boilerplate code, and refactoring. 3. Image and video generation Bing, image creator, DALL-E, stable diffusion for design, ads, prototypes, or entertainment. 4th, conversational agents and chatbots, AI assistants in Microsoft Teams, customer support bots, personal productivity tools. 5th, data augmentation and simulation, generating synthetic data for training other AI models in domains like healthcare or finance. 6. Personalization, custom product recommendations, personalized learning material, adaptive marketing. 7. Creative industries music composition, video game asset creation, screenplay assistance. 8. Healthcare and science drug molecule generation, medical image synthesis for research, automated clinical documentation. In short, any domain where creating new, context-aware, and high-quality output matters is a candidate for generative AI. Describe the differences between supervised, unsupervised, and self-supervised learning. Supervised learning is a type of machine learning where the model is trained on labeled data, meaning each input comes with a known correct output. The goal is for the model to learn a mapping from inputs to outputs, such as predicting house prices based on features like size, location, and age. Unsupervised learning is where the model is trained on unlabeled data. There are no predefined answers. Instead, the model tries to discover hidden patterns or structures within the data, such as grouping customers with similar purchasing behavior through clustering. Self-supervised learning is a newer paradigm where the data is also unlabeled, but the system generates its own labels from the raw data to create supervised-like tasks. A common example is in large language models, where certain words in a sentence are masked, and the model learns to predict them. This approach has become the foundation for training modern generative AI models like GPT, BERT, and CLIP. What are some common loss functions used in generative models? Generative models use different loss functions depending on the architecture and the type of output they are generating, but several are widely used across the field. In language models like GPT, the most common loss is the cross-entropy loss, which measures how well the predicted probability distribution over tokens matches the actual next token. It's essentially teaching the model to assign high probability to the correct outputs. In autoencoders and VAEs, we often use reconstruction loss, typically mean squared error, MSE, for continuous data or cross-entropy for discrete data, to ensure the output matches the original input. In VAEs, this is combined with a Kullback-Leibler, KL divergence loss, which regularizes the learned latent space to follow a desired probability distribution. In GANs, the defining loss is the adversarial loss, where a generator tries to produce outputs that fool a discriminator, and the discriminator learns to distinguish real from fake. This is often implemented as a minimax objective, sometimes with variations like Wasserstein loss for more stable training. In diffusion models, the loss is usually a noise prediction loss, often mean squared error between the predicted noise and the actual noise added during the forward diffusion process. In short, cross-entropy for sequence generation, reconstruction plus KL divergence for VAEs, adversarial for GANs, and noise prediction for diffusion models. Each tailored to the specific way the generative model learns its data distribution. What is representation learning, and why is it important for generative AI? Representation learning is the process by which a model automatically discovers and learns useful features from raw data. Rather than relying on handcrafted features designed by humans, in other words, the model learns to represent the data in a way that captures its most important characteristics and relationships. In generative AI, representation learning is critical because the quality of what the model generates depends on how well it understands and encodes the underlying structure of the data. For example, in a large language model, the learned representations capture grammar, semantics, and context. In an image model, they capture shapes, textures, and spatial relationships. Good representations make it possible for the generative model to create outputs that are coherent, realistic, and contextually relevant. They also allow the model to generalize, meaning it can create new content it has never seen before, while still making it consistent with the patterns it learned from training data. Without strong representation learning, a generative model might simply memorize data instead of understanding it, leading to poor creativity, overfitting, or unrealistic outputs. What are latent variables, and how are they used in generative models? Latent variables are hidden or unobserved variables that capture the underlying structure or factors in data which aren't directly measurable. They act as a compressed, abstract representation of the input, holding essential information needed to reconstruct or generate new samples. In generative models, latent variables serve as the creative space from which the model draws when producing new outputs. For example, in a variational autoencoder, VAE, an encoder maps input data into a latent space, a lower-dimensional representation that captures its key features. The decoder then samples from this space to reconstruct the input or generate entirely new variations. In GANs, the generator takes a random vector from a latent space and transforms it into realistic data, like an image. The structure of the latent space often determines how controllable and diverse the generated content is. Latent variables are important because they allow generative models to separate meaningful factors of variation such as style, shape, or color, and recombine them in novel ways, enabling creativity, interpolation between examples, and more efficient learning from data. Explain the difference between batch and online learning. Batch learning and online learning differ in how they process and update models with data. Batch learning is when the model is trained on the entire dataset at once, or in large chunks called batches. The model only updates its parameters after seeing the full dataset, or each batch in mini-batch training. This approach is common when the dataset is fixed and available beforehand, for example, training a GPT model on a large static corpus. Batch learning often achieves high accuracy, but can be resource-intensive and slower to adapt to new data. Online learning is when the model updates its parameters incrementally as each new data point, or a small set of points, arrives. This makes it ideal for streaming or real-time scenarios where data comes continuously, such as clickstream analysis or stock price prediction. Online learning can adapt quickly to changes in data distribution but may be more sensitive to noise. In short, batch learning is like studying an entire textbook before taking a test, while online learning is like updating your knowledge page by page as you read new information. What is a generative adversarial network, GAN? A generative adversarial network, or GAN, is a type of generative model introduced by Ian Goodfellow in 2014 that learns to create realistic synthetic data through a game between two neural networks, the generator and the discriminator. The generator takes random noise, a vector from a latent space, and transforms it into synthetic data, such as an image. The discriminator receives both real data from the training set and fake data from the generator, and its job is to distinguish between the two. During training, the generator tries to fool the discriminator, while the discriminator tries to catch the generator's fakes. This creates a minimax game. The generator improves at producing realistic data. The discriminator improves at detecting fakes. Training continues until the generator's outputs are so convincing that the discriminator can't reliably tell real from fake. GANs are powerful because they can produce highly realistic images, videos, and even audio, used in applications like deepfakes, super-resolution imaging, art creation, and data augmentation. How do the generator and discriminator work together? In a GAN, the generator and discriminator work together in a competitive yet complementary way, forming what's called an adversarial learning process. The generator starts with random noise from a latent space and tries to transform it into synthetic data that looks as real as possible. Its goal is to fool the discriminator into thinking its outputs are real. The discriminator receives both real samples from the training dataset and fake samples from the generator. It learns to output a probability score high for real data, low for fake data. During training, both networks improve simultaneously. If the discriminator easily spots fakes, the generator gets feedback on how to make its outputs more realistic. If the generator produces convincing fakes, the discriminator must improve to detect them. This back and forth creates a minimax optimization game. The generator minimizes the probability of the discriminator catching its fakes. The discriminator maximizes the probability of correctly classifying real versus fake. Over time, this dynamic pushes the generator to produce outputs that are indistinguishable from real data, while the discriminator becomes an expert at detecting subtle imperfections until it can no longer reliably tell the difference. What problems do GANs solve particularly well, and what are their key limitations? GANs excel at generating highly realistic, high-quality synthetic data that closely mimics real-world data distributions. They are particularly effective in areas like image synthesis, creating photorealistic faces, objects, or scenes; image-to-image translation, converting sketches to images, day to night, or low-res to high-res; data augmentation, producing synthetic samples to improve training for other models; creative applications, AI art, fashion design, game assets; super resolution, sharpening and upscaling low-quality images. The core strength of GANs lies in their ability to model complex, high-dimensional data distributions without explicitly defining them, learning directly from raw examples. However, GANs also have key limitations. Training instability. The adversarial game can oscillate or collapse if not balanced. Mode collapse. The generator may produce limited variety, repeating similar outputs. Data hunger requires large, diverse datasets for good performance. No inherent likelihood estimation. Unlike some generative models, GANs can't easily tell you how probable a given sample is. High compute cost. Training can be expensive and slow. In short, GANs are exceptional for producing realistic, domain-specific synthetic content, but they require careful architecture design, tuning, and large datasets to overcome instability and collapse. How do you stabilize GAN training? Stabilizing GAN training is crucial because the generator-discriminator game can be highly unstable, leading to issues like mode collapse, vanishing gradients, or oscillations. Several proven techniques can make training more stable and reliable. 1. Use Wasserstein GAN, WGAN, replaces the standard adversarial loss with the Wasserstein distance, providing smoother gradients and better convergence. Often combined with gradient penalty to enforce Lipschitz continuity. 2. Label smoothing. Instead of labeling real samples as exactly 1, use slightly lower values, example 0.9, to prevent the discriminator from becoming overconfident. Third feature, matching. Make the generator match intermediate feature statistics from the discriminator, not just its final output, to reduce mode collapse. Fourth, mini-batch discrimination. Allow the discriminator to look at batches of samples together, detecting lack of diversity in the generator's outputs. 5. Progressive growing. Start training at low resolution and gradually increase image size, which helps the generator learn structure before fine details. 6. Balanced training. Avoid letting the discriminator overpower the generator by updating them in balanced steps. Example, 1-to-1 or tuned ratios. 7. Regularization techniques. Apply spectral normalization, weight clipping, or dropout to improve generalization and prevent overfitting. The main principle is to keep the adversarial game fair. Neither network should dominate for too long, and both should receive stable informative gradients so they can improve together. What is a variational autoencoder, or VAE? A variational autoencoder, or VAE, is a type of generative model that learns to encode input data into a structured, continuous latent space, and then decode from that space to reconstruct or generate new data. It extends the basic autoencoder by making the latent space probabilistic rather than fixed. Instead of mapping each input to a single point, the encoder produces a mean and variance that define a probability distribution for each latent variable. During training, we sample from this distribution and pass it to the decoder, which reconstructs the data. The VAE is trained with a loss function that combines 1. Reconstruction loss ensures the output is close to the original input. Second KL divergence loss regularizes the latent space to follow a known distribution, usually Gaussian, making it smooth and continuous. This structured latent space allows VAEs to smoothly interpolate between data points, generate variations of inputs, and explore new combinations of learned features. They're widely used for image synthesis, anomaly detection, data compression, and as building blocks for more complex generative models. How do VAEs differ from GANs? VAEs and GANs are both generative models, but they take fundamentally different approaches to learning and generating data. A VAE is a probabilistic encoder-decoder model. It explicitly learns the probability distribution of the data by mapping inputs into a continuous latent space and sampling from it. The training objective combines reconstruction loss with KL divergence to ensure the latent space is smooth and well-structured. VAEs tend to produce outputs that are more diverse and interpretable, but often slightly blurrier because they optimize for average reconstruction quality. A GAN, on the other hand, is a game between two networks, a generator that produces synthetic data from random noise, and a discriminator that tries to distinguish real from fake. GANs learn implicitly, without explicitly modeling probability distributions, and often produce sharper, more realistic outputs. However, they can suffer from instability, mode collapse, and lack of diversity. In short, VAE, probabilistic, stable training, diverse outputs, slightly less sharp. GAN, adversarial, potentially unstable, very sharp outputs, may lack diversity. What is a diffusion model? How do denoising diffusion probabilistic models, DDPMs, work? A diffusion model is a generative model that creates data by reversing a gradual noising process. Instead of learning to map noise directly into an output, it learns how to denoise step by step until a high-quality sample emerges. A denoising diffusion probabilistic model, DDPM, works in two phases. 1. Forward diffusion process. Starting from real data, the model gradually adds Gaussian noise over many small steps until the data becomes pure noise. This process is fixed and not learned. 2. Reverse denoising process. The model is trained to reverse this process. Starting from pure noise, it learns to predict and remove the noise at each step, eventually reconstructing a realistic sample. This is done using a neural network, often a U-net with attention, trained with a noise prediction loss, typically mean squared error between predicted and actual noise. Because the denoising happens in small steps, DDPMs can generate very high-quality, diverse samples often rivaling or surpassing GANs in fidelity and stability. They're widely used in text-to-image systems like DALL-E 2 and Stable Diffusion, where text encoders guide the denoising process to produce images aligned with a prompt. The key strengths of diffusion models are their stability in training, ability to capture complex data distributions, and high controllability when combined with conditioning methods like classifier-free guidance. Compare and contrast GANs, VAEs, and diffusion models. GANs, VAEs, and diffusion models are all generative models, but they differ in how they learn data distributions, their output quality, and training behavior. GANs work through an adversarial game between a generator and discriminator. They excel at producing sharp, realistic images, but can be unstable to train and prone to mode collapse. They don't explicitly model probability distributions, so likelihood estimation is not straightforward. VAEs are probabilistic encoder-decoder models that explicitly learn a structured latent space. They are stable to train, good for interpolation, and generate diverse outputs. However, because they optimize for average reconstruction quality, outputs can appear slightly blurry compared to GANs. Diffusion models learn to reverse a gradual noising process, generating data step by denoising. They are highly stable, produce state-of-the-art quality images, and offer strong diversity and controllability. Their main drawback is slower generation due to many denoising steps, though newer techniques are speeding this up. In short, GANs, adversarial, sharp outputs, unstable, diversity issues. VAEs, probabilistic, diverse, interpretable latent space, slightly blurry. Diffusion, step-by-step denoising, very high quality and diverse, stable, slower to sample. What is the role of noise in generative modeling? Noise plays a crucial role in generative modeling because it introduces randomness and variability, allowing models to generate diverse outputs rather than deterministic copies of the training data. In models like GANs, random noise vectors sampled from a latent distribution, example Gaussian, serve as the seed for the generator. This noise encodes variability. Changing it produces different outputs, while still following the learned data distribution. In VAEs, noise is injected when sampling from the learned latent distribution during training and generation. This allows smooth interpolation between points in latent space and helps the model generalize beyond memorizing training data. In diffusion models, noise is central to the process. The forward phase gradually adds Gaussian noise to corrupt the data, and the reverse phase learns to remove it step by step. The model essentially learns the structure of data by predicting the noise added at each step. Overall, Noise acts as the starting point for creativity in generative models. It's what lets them imagine countless new variations rather than reproducing the same patterns over and over. What is an autoregressive model? An autoregressive model is a type of generative model that generates data one step at a time, with each new step conditioned on the outputs generated so far. In the context of text generation, the model predicts the probability distribution of the next token given all previous tokens. Mathematically, it factorizes the joint probability of a sequence into a product of conditional probabilities. For example, GPT models are autoregressive. They start with a prompt, predict the first token, then feed that token back in to predict the next, and so on until the sequence is complete. Autoregressive modeling isn't limited to text. It's also used in speech synthesis, time series forecasting, and image generation by generating pixels or patches sequentially. The main strength is high-quality, coherent outputs because each prediction considers the full history. The drawback is that generation is inherently sequential and can be slower compared to parallel methods, and errors can accumulate as predictions build on past outputs. How does a transformer model contribute to generative AI? The transformer model is the backbone of most modern generative AI systems because it excels at modeling long-range dependencies and contextual relationships in data, whether text, images, audio, or code. Its key innovation is the self-attention mechanism, which allows the model to look at every position in the input sequence and weigh its relevance when predicting the next output. This means the model can capture global context efficiently, unlike older RNNs or LSTMs, which process data sequentially and struggle with long-term dependencies. In generative AI, transformers make it possible to generate coherent long-form text, example GPT models in ChatGPT, create detailed images from text prompts when combined with diffusion models, example DALL-E2 Stable Diffusion's text encoders, generate code, music, or multimodal outputs by learning complex cross-domain relationships. Transformers also scale extremely well. Their parallelizable architecture allows training on massive datasets, which is why today's generative models can handle billions of parameters. In short, the transformer brought generative AI into its modern era by enabling high-quality, context-aware generation at scale. What is an energy-based model, EBM, and how does it differ from GANs and VAEs? An energy-based model, EBM, is a generative modeling framework that learns to assign a scalar energy score to each possible configuration of variables. Lower energy for more likely or realistic configurations, and higher energy for unlikely ones. The goal is to shape the energy landscape so that real data points sit in low-energy regions, while unrealistic ones are in high-energy regions. Unlike GANs, EBMs don't require a separate discriminator-generator adversarial setup. Instead, they directly learn an energy function and often use sampling methods like Markov chain Monte Carlo to generate new data from low-energy regions. EBMs can model complex, multimodal distributions, but can be slower to sample due to iterative sampling steps. Compared to VAEs, EBMs don't need an explicit encoder-decoder structure or a fixed latent space distribution. VAEs optimize a variational lower bound with a probabilistic latent variable model, while EBMs focus on shaping an energy function over the data space. In short, EBMs learn an energy function, flexible but slower sampling. GANs, adversarial training, sharp outputs, no explicit likelihood. VAEs, probabilistic latent space, stable training, diverse but sometimes blurry outputs. Which models are most commonly used for text generation? The most commonly used models for text generation today are transformer-based autoregressive language models, such as GPT, Generative Pre-trained Transformer, PaLM, and LLM. These models generate text one token at a time, conditioning each prediction on the previously generated tokens, which ensures high coherence over long passages. Historically, text generation used RNNs and LSTMs, but they struggled with long-range dependencies and scalability. Transformers replaced them thanks to the self-attention mechanism, which captures global context efficiently and trains in parallel. Other notable architectures include T5 or BART, encoder-decoder transformers that excel at conditional text generation tasks like summarization or translation. XLNet, a permutation-based transformer that improves bidirectional context modeling while retaining autoregressive generation. Mixture of experts models like Mixtral, which scale up generation by dynamically routing to specialized submodels. In short, while there are many variations, decoder-only transformers like GPT dominate free-form text generation, and encoder-decoder transformers lead in controlled, task-specific generation. What is neural style transfer? Neural style transfer is a deep learning technique that takes the content of one image and the artistic style of another, and blends them to create a new image that preserves the content while adopting the style. It works by using a pre-trained convolutional neural network, CNN, often VGG, to extract feature representations from both the content image and the style image. The content representation comes from higher layers of the network, capturing shapes and structures. The style representation is captured using gram matrices from lower and mid-level layers, which reflect textures, colors, and patterns. The algorithm then starts with a random or content-based image and iteratively updates it to minimize two losses. 1. Content loss keeps the generated image similar in structure to the content image. 2. Style loss matches the texture and color patterns to the style image. Neural style transfer has been used for creating digital art, transforming photos into paintings in the style of artists like Van Gogh or Picasso, and even for video stylization. How can you use generative models for image super-resolution? Generative models can be used for image super-resolution by learning to reconstruct a high-resolution, HR, image from its low-resolution, LR, counterpart, effectively adding plausible fine details that were not present in the original. A common approach is to use GAN-based architectures such as sRGAN or EsRGAN. In these, the generator takes an LR image and predicts an HR version, while the discriminator learns to distinguish between real HR images and generated ones. The adversarial loss encourages the generator to produce sharper, more photorealistic textures, while a content loss, often based on VGG feature maps, ensures structural similarity to the ground truth. Other methods include diffusion models, trained to denoise and add detail in progressive steps, producing high-quality HR images from LR inputs. VAEs can learn a latent representation of HR images and decode LR inputs into HR outputs, though they may be slightly blurrier. Generative models are preferred over simple interpolation, like bicubic upscaling, because they can hallucinate realistic high-frequency details, making the result visually convincing while staying faithful to the content of the original. What are the main challenges in generating music with AI? Generating music with AI is challenging because it requires balancing creativity, structure, and coherence over long time spans while working with complex, multidimensional data. Some of the main challenges are: 1. Long-term structure. Music depends on patterns that can span minutes, including motifs, chord progressions, and thematic repetition. Many models struggle to maintain coherence over long sequences. 2. Multimodal complexity. Music has multiple layers, melody, harmony, rhythm, dynamics, timbre, that need to be generated in coordination. Three-point representation choice, deciding whether to model music as raw audio waveforms, spectrograms, MIDI sequences, or symbolic notation greatly affects quality and generation speed. Fourth, style control. It's difficult to precisely control genre, instrumentation, mood, or structure without detailed conditioning mechanisms. 5. Evaluation. Unlike text or images, music quality is subjective, making automated evaluation metrics harder to design. 6th, data limitations and copyright. High-quality, diverse, and legally usable music datasets are limited, and copyright concerns are significant. In short, generating music with AI is not just about producing pleasant sound. It's about maintaining musical logic, stylistic control, and emotional resonance while respecting technical and legal constraints.
You've just unlocked the skills most candidates never prepare for. If you're serious about landing your dream AI role, don't stop here, watch the next part, and make sure to subscribe so you never miss the knowledge that could change your career.